Every second, the universe is running code we can't read. You think science has it figured out? We can land robots on Mars, edit DNA, and build chips with transistors thinner than a virus. But when you zoom in close enough, when you actually look at what reality is made of, physics stops giving answers and starts giving riddles. Quantum mechanics is the most successful theory in human history. It predicts the behavior of particles to 12 decimal places. It powers your phone, your lasers, your entire digital world. And yet, after nearly a century, nobody, not one physicist on Earth, can tell you what it actually means. Welcome to the Edge of Understanding. Here are 12 quantum mysteries science still can't explain.
Before we break reality together, if you're the kind of person who stays up at 2 a.m. wondering why anything exists, this channel was built for you. Hit subscribe, turn on notifications, not because I asked, but because the algorithm buries this kind of content, and we both know you're tired of surface-level explainers. Let's go deeper. Number 1, the measurement problem. Here's the setup. A quantum particle, an electron, a photon, whatever, exists as a wave of probability. It's not here or there. It's here and there, in a superposition of all possible states, until something measures it. Then, snap, it collapses into one definite outcome. But here's the question that keeps Nobel laureates awake. What counts as a measurement? Is it a conscious observer? A machine? A stray air molecule bumping into the particle? The math is silent. The theory works perfectly if you just assume collapse happens, but it never explains why or when. Copenhagen interpretation says, don't ask, just calculate. Many worlds says it never collapses. Every outcome happens in a branching universe. Objective collapse models say gravity does it. But here's the kicker. After a century of debate, there is zero experimental evidence that definitively favors one interpretation over another. The measurement problem isn't a small hole in quantum mechanics. It's a canyon, and we're still building the bridge.
Number 2, quantum entanglement. Einstein called it spooky action at a distance. He hated it. Two particles can be linked so intimately that measuring one instantaneously determines the state of the other, no matter how far apart they are. In 2022, the Nobel Prize in Physics went to experiments proving this isn't a theory, it's real. Entangled particles violate Bell's inequalities. Local hidden variables are dead. But here's the mystery. How does the information get from particle A to particle B? It doesn't travel through space. It doesn't take time. It doesn't use any known force or field. And crucially, you can't use it to send a message faster than light, so causality stays intact. But the correlation itself, it's there. It's tested. It's undeniable. We can use entanglement for quantum computing and unhackable encryption, but ask a physicist why two particles separated by light years behave like one object, and you'll get a shrug wrapped in advanced mathematics.
Number 3, wave-particle duality. You fire one electron at a time through 2 slits. Individually, each electron hits the detector like a particle, a single point. But over thousands of shots, they build up an interference pattern, as if each one passed through both slits as a wave and interfered with itself. But if you watch which slit it goes through, the interference vanishes. It acts like a particle again. This isn't a technological limitation. It's built into reality. The act of gaining which path information destroys the wave behavior, even if you look after the particle passed the slits. Delayed choice quantum eraser experiments confirm this. The universe seems to care whether you're paying attention, and we have no idea why. Number 4, the arrow of time. Time moves forward. Eggs don't unbreak. Heat flows from hot to cold. This is entropy, and it's the second law of thermodynamics. But here's the quantum problem. The fundamental equations of quantum mechanics are time-symmetric. They work just as well backward as forward. So where does time's arrow come from? Some physicists argue it's about the initial conditions of the Big Bang, an extremely low entropy state that everything is still relaxing from. Others say it's an emergent property, not fundamental, like temperature. But in quantum gravity, where space-time itself might be quantized, the concept of time becomes deeply problematic. In quantum mechanics, time is a background parameter, a clock on the wall. In general relativity, time is part of space-time geometry, bending with gravity and velocity. These two pictures of time are fundamentally incompatible. We experience time, we measure time, but we cannot explain why time has a direction, or even if it truly exists at the quantum level.
Number 5. Quantum gravity. General relativity describes gravity as the curvature of space-time. It's beautiful. It's tested to extraordinary precision. Quantum field theory describes the other three forces as exchanges of force-carrying particles. It's the most accurate theory ever devised. Put them in the same room, and they destroy each other. At the Planck scale, 10 to the minus 35 meters, the energy density needed to probe quantum gravity creates a black hole. The theories produce infinities. They're mathematically incompatible. String theory tries to solve this by replacing point particles with vibrating strings in higher dimensions. Loop quantum gravity tries to quantize space-time itself into discrete chunks. Neither has experimental confirmation. Neither can make a testable prediction that distinguishes it from the other. Black holes are where this conflict becomes unavoidable. A black hole's singularity is a point where general relativity says space-time curvature becomes infinite, and quantum mechanics says that's impossible because nothing can be localized that precisely. We need quantum gravity to understand the Big Bang, black holes, and the ultimate nature of space and time. And we don't have it.
Number 6. The black hole information paradox. Stephen Hawking proved that black holes emit radiation, Hawking radiation, and slowly evaporate. But here's the problem. Hawking's calculation says this radiation is perfectly thermal. It contains no information about what fell into the black hole. But quantum mechanics says information is never destroyed. It can be scrambled, hidden, encoded, but never erased. If black holes destroy information, quantum mechanics is wrong. If they don't, we need a mechanism to explain how information escapes. This isn't philosophical. In 2019, the black hole information paradox exploded back into the headlines when researchers showed that if you follow the math carefully, the paradox gets worse than we thought, not better. Some propose that information is encoded in subtle correlations in the Hawking radiation. Others suggest a firewall at the event horizon that destroys anything that falls in. Others say the information never enters the black hole in the first place. It's encoded on the horizon via the holographic principle. Every solution breaks something else we thought was true.
Number 7. The cosmological constant problem. Quantum field theory predicts that empty space should have energy, vacuum energy. Every field fluctuates even in the vacuum. Add up those fluctuations and you get a massive number. Observations say the actual energy of empty space, the cosmological constant driving dark energy, is tiny. Positive, but tiny. The mismatch? About 120 orders of magnitude. That's a 1 followed by 120 zeros. This is not a rounding error. This is the worst prediction in the history of physics. If the vacuum energy were what quantum field theory naively predicts, the universe would have expanded so fast that no structures, no galaxies, no stars, no atoms could ever form. Something cancels it out almost perfectly, but not quite. We have no idea what that something is. Supersymmetry could do it, but we haven't found supersymmetric particles at the LHC.
The universe should be a vacuum energy hellscape. Instead, it's habitable, and we don't know why. Number 8. The strong CP problem. CP symmetry means the laws of physics look the same if you swap particles for antiparticles, C, and flip space like a mirror, P. The weak force violates CP. That's well established. But the strong force, the force that binds quarks into protons and neutrons, should violate CP too. The math allows it. There's a term in the QCD Lagrangian that could create CP violation in strong interactions. Experiments say it doesn't. The neutron electric dipole moment is measured to be staggeringly small, consistent with zero. So, nature had a choice. CP violation in the strong force was allowed, but the parameter is tuned to nearly zero. Not exactly zero, we can't prove that, but so close to zero that it looks suspiciously like something is protecting it. The leading explanation is the axion, a hypothetical particle that dynamically drives the CP violating parameter to zero. And here's the bonus. Axions are also a leading dark matter candidate. But we haven't found the axion. The strong CP problem remains open, and the tuning is so precise that it feels less like a coincidence and more like a clue we're missing. Number 9. The hierarchy problem. The Higgs boson gives other particles mass. We found it at the LHC in 2012. Its mass is about 125 GeV. Here's the mystery. In quantum field theory, particles get mass corrections from virtual particles popping in and out of the vacuum. The Higgs should get corrections from physics at every energy scale, including the Planck scale, where quantum gravity lives. Those corrections should blow the Higgs mass up to the Planck scale, 10 to the 19th GeV. But it's 125 GeV. That means something cancels those corrections with exquisite precision. Supersymmetry was the leading candidate. Every particle gets a superpartner that cancels its partner's quantum corrections precision. But the LHC has found no superpartners up to 13 TeV. Other ideas include extra dimensions, composite Higgs models, or the anthropic principle. We're in a universe with a light Higgs because otherwise we wouldn't be here to ask. But none of these are confirmed. The hierarchy problem is a neon sign pointing to physics beyond the standard model, and we're still in the dark. Number 10. Decoherence versus collapse. Here's a popular answer to the measurement problem. Decoherence. When a quantum system interacts with its environment, air molecules, photons, anything, the superposition doesn't collapse. It just becomes entangled with the environment. The phases that create interference get scrambled. The system looks classical because you can't practically measure the interference anymore. But decoherence doesn't solve the measurement problem. It explains why superpositions are hard to observe in large systems. It does not explain why you see one outcome and not another. The wave function, mathematically, still contains all branches. Decoherence just hides them from you. So does the universe split? Does consciousness select? Does gravity collapse it? Decoherence tells us how classicality emerges. It does not tell us why one specific outcome becomes real. The line between quantum and classical is still drawn in pencil. Non-locality and relativity. Entanglement is non-local. Measure particle A and particle B's state is determined instantly, even if it's on the other side of the universe. This seems to violate Einstein's principle that nothing can influence anything else faster than light. But careful analysis shows you can't use entanglement to send information faster than light. The correlation is there, but it's not usable for signaling. So special relativity isn't violated. But here's the deeper mystery. How does the universe enforce this? What mechanism ensures that non-local correlations exist but cannot be exploited for faster-than-light communication? The no-signaling theorem is a mathematical fact, but it's not an explanation. It's as if the universe allows spooky action at a distance, but installs a failsafe to prevent paradox. Why? We have no idea.
Number 12, the interpretation of quantum mechanics. This is the meta mystery. Quantum mechanics works. It predicts, it engineers. But ask 10 physicists what the wave function is, and you'll get 10 different answers. Copenhagen says it's a tool for calculating probabilities, full stop. Many Worlds says it's a real branching multiverse. Pilot wave theory says particles have definite positions, guided by a real wave. Cubism says it's an agent's subjective belief. Relational quantum mechanics says properties are relative to the observer. These interpretations make different claims about reality. Some are deterministic, some inherently probabilistic. Some require infinite parallel universes, others require none. And here's the crucial point. As of 2026, no experiment has definitively ruled out any major interpretation. They all predict the same experimental outcomes. The difference is purely philosophical. Except it's not, because what you think quantum mechanics means determines what kind of theories you pursue, what experiments you design, and what questions you think are worth asking. We have a theory that describes everything and explains nothing.
12 mysteries, 12 cracks in the foundation. And here's the truth. Every single one of these problems is connected. Solve the measurement problem, and you might solve the black hole information paradox. Crack quantum gravity, and the arrow of time might make sense. Find the axion, and you solve both the strong CP problem and dark matter. Physics isn't a collection of isolated puzzles. It's one giant equation with missing terms, and we're still learning how to read it. The universe is not required to make sense to us, but it is required to be consistent. And somewhere in the space between those two requirements, the next revolution is waiting.
If your brain hurts right now, good. That means you're thinking at the edge of what we know. And if you want to keep going, if you want to see what happens when we take that same statistical rigor and apply it to the cosmos itself, my next video is for you. It's called 6 Alien Scenarios Scientists Say Are Statistically Possible. We're talking Dyson spheres, von Neumann probes, and contact scenarios that actual astrophysicists have run the numbers on. Not sci-fi, statistics. The math says these things could happen, and some of them, they might already be happening. Links in the description. It'll autoplay when this ends if you've got autoplay on. Either way, don't let the algorithm decide what you watch next. I'll see you there.